Hello guys and welcome to another video with Cass on the Mismo channel. So today we're going to take a look at some solutions for the diagnostic pulse generator. So I have a bunch of them here and they have very interesting features that I would like to show you guys. Let's start with the basic one, which I'm calling the basic inverter. So the board has just one input for a button and an output called pulse. And if we look at the verification tab, what this puzzle expects us to do is for as long as the button is pressed, we need to output this wave pattern that you see down here. And that's basically it. Alright, so the basic solution here basically copies the value of the accumulator to P1, which is the output. Sleeps for 1 second, and then it checks for the button, which is P0. So if it's not pressed, if it's greater than 0 here, so if it's pressed, then we invert the value of the accumulator, and then we output it. So it's going to change from 0 to 100, and then sleep for 1 second, then from 100 to 0, sleep for 1 second, and so on. So this will create this wave pattern. And as soon as the button is not pressed anymore, we fall into this instruction here, which moves 0 into the accumulator to guarantee that the output will be 0 next time. We do this because if you hold your button pressed for a even number of time units, it will end up being 0 anyways, but in other case it will end up being 100, which will break this thing. So yeah, if we advance in here, you can see that it will output everything correctly. So this is not a very interesting solution, so let's take a look at something else. Alright, so the basic solution has a total cost of 3, uses 238 power and 5 lines of code in total. So next up, I would like to show you this solution here. Same costs, but very low power usage, and only 3 lines of code. So yeah, a great solution. So yeah, let's see what is going on here. So it uses the gen, which is the secret instruction. So yeah, it's a little bit of a spoiler if you're not that far in the game. And what it does is it checks if the button is pressed, and if it is, we use the gen instruction to create one little pulse like this. So 1 time unit, the signal goes high, and 1 time unit, the signal goes low, and then it cycles again. And if the button is still pressed, we do this over and over again. This is cool because we don't need to reset it to end up being 0 all the time, because it does this automatically. And if the button is not pressed, we basically sleep and check if the button is pressed, and sleep and sleep and sleep. So this is why this solution is very power efficient. So let's maybe run the entire thing in here. Let me show you this. So if we step with the function, you can see like if the button is pressed, we are basically executing only one instruction. So look now, the wave pattern shows that the button is not going to be pressed anymore. And check this out. Sleep, sleep, sleep. So this is a really awesome solution. Next up, I have something very exciting to show you, which is a solution that uses only 1 line of code, guys. That's right. It's a little bit more expensive because I use another component called the mux, and I think because of that, it draws more power, but it's only 1 line of code. So let's take a look at this magic solution. And there it is, guys, in all its glory. So this component is a input expander, or a mux. I can maybe quickly explain this to you. And then the one instruction is a gen that we generate on P1, which is the output. And the output is supposed to be on for x0 time units, and then off for 1 unit. And the magic thing is x0 will be 1 when the button is activated. So it will do exactly what the 3-line solution did, the one I just showed you. And if the button is not pressed, it's going to be on for 0 time units, which means it's going to be only off for 1 time unit, making this instruction work the same as sleep, so sleep 1. And the reason why we have this mux here instead of just this signal connecting directly in there, it should be something like this, right? Is because when the button is activated, this guy would get a 100 as input. So if we read P0, if the connection is right and everything, it reads 100. So this would be on for 100 cycles and then off for 1 cycle. But we want this to happen. When the button's pressed, we want the instruction to work like this, and when the button's not pressed, we want the instruction to be like this. And if you don't know how this thing works, let's just get everything in place in here. So you can see that it has 3 inputs, so P0, P1, and P2. And if we try to read this device from the X0 port, we will read a 3-digit number that goes like this: P2, P1, P0, right? So for instance, if those two are connected and this one is not connected. So if these two are powered, but not this one, it will read something like this: 1, 1, 0. So when the button powers P0, it's going to read 0 from P2, 0 from P1, and 1 from P0, right? So yeah, maybe my explanation is a little bit confusing, but you guys get the idea. We're basically converting 100 into 1 using hardware instead of software. And this is how the solution works. Yeah, let's maybe take a look at how this simulates. So yeah, pretty nicely. You see how the power goes. Very nice solution. Finally, I want to show you guys 2 alternative solutions just out of curiosity. And the first one is this gates only. So it uses 0 lines of code. This is not my solution. I got it from Reddit, I think, or maybe from Steam. I'm not sure. But this thing doesn't work anymore, guys, because gates have no delay. So the game has changed. So this is a very old solution. If anyone knows how to make this solution still work for any reason, you can comment on this video. Yeah, but other than that, I also have a FPGA solution that uses something called a micropulse. Which, well, there's probably a tutorial available on my channel if you don't know what micropulses are. So basically here, when the button's pressed, we send a micropulse every tick, and this guy works as a T flip-flop. So this FPGA can be anything, right? So I configured the FPGA to become a T flip-flop. So we send it a micropulse, it switches, and when it switches, it does the pattern that we expect it to do. So just like this. Yeah, just so you guys can see it working. I won't get in too much detail because as you can see here, this solution is more expensive, uses tons of extra power and more lines of code compared to everything. So it's just a concept, just to show how FPGAs could be used to solve this problem, but it's worse in every aspect that you can think of. Alright guys, I can't wait to show you my next solutions to the next puzzles. Thank you very much for watching. Feedback is always appreciated, and goodbye.